Hello and welcome to this short video about the mathematical constant E. So for those of you who are unaware, E is approximately 2.718281828 and so on. It is not 1828 repeating also, by the way, that's just a coincidence here. It happens that 1828 has repeated twice, but in fact E is an irrational number. It has infinite number of digits continuing to the right side here, but it's approximately 2.718281828. So, to start talking about E, I would like to introduce you to this simple question. Let's say we have a magical bank. This is a hypothetical bank somewhere. This bank has a certain way of calculating interest and a certain way of giving you interest rates for fixed deposits. So let's say you go to this bank and you deposit $1. You deposit $1. And when you deposit $1, the bank clerk comes and tells you, alright sir, how would you like to have your interest given for this $1? And he says, there's two things you could do. You could either receive 100% interest per annum, which by the way, if a bank ever tells you that you can have 100% interest per annum, either the bank is in serious trouble or your economy is in serious trouble. No bank would ever give you 100% interest unless they are in serious trouble. But let's just imagine that this magical bank gives you 100% interest per annum. So every year you would gain 100% of what you had in the previous year. So in this case, your $1 would then become $2 in total. But then he gives you another offer. He says, I can split this 100% interest per year into a certain number of pieces. Let's say he says first, I will split this 100% interest per year into two pieces of 50%, and I'll split the time period that you need to wait in order to get that interest also by 50%. So what he means is, I will give you 50% interest, but I'll give it to you like 100 divided by 2 is percent interest, but I'll give it to you in a year divided by 2 times, so per 6 months. So he's giving you these two offers. Now think about it and tell me which of these offers should you take. Considering the fact that this is compound interest we're dealing with, because it's a bank, of course, banks don't tend to deal in simple interest. This bank deals in compound interest, which means the first offer after 1 year will make you $1 times 1 plus 100% of 100%, and that means you'll get $1 times 1 plus 1, which is $1 times 2, which is $2. How about the second offer? Well, what the second offer is doing is converting your $1 after 6 months into $1 times 1 plus a 50% of 100%, and then that gives you $1.5. But then after another 6 months at the end of the year, again you have to multiply this same amount by a certain extra more interest that you will receive, which is another 1 plus 50% over 100%. So 1.5 times 1 plus 50% divided by 100% is 1.5 times 1.5, which is $2.25. So it seems that it is better to take offer number 2. If you take offer number 2, you make $0.25 or a quarter more money than you would have if you just took the 100% interest per annum. So you say, alright, I'll take the second offer. But then he comes back and he gives you a third offer. He says, alright, instead, what if I give you 33.3 repeating percent interest, but I give you that interest in 1 year divided by 3 periods of time. So 1 year divided by 3 is 4 months. So he'll give you 33.3 repeating percent interest per 4 months. Now you have to think about this again. Is this third offer, I'll label it offer 3, is offer 3 better than offer 2? So if you do this calculation again, this time what we have is $1 times 1 plus 33.3% repeating divided by 100%. We have to do that once after 4 months, and then we have to do it again after another 4 months, which means we have to square it, and then we have to do it again after another 4 months, which means we have to cube it. So this is the actual number that we are looking for, this is the final amount of money you will have after 1 year. So I'm not going to do this calculation, I've already done it, and this amount is approximately $2.370. So it looks like again the third offer is better than the second offer. So you say, alright, I'll take the third offer. And then he comes back again and he says, what if, sir, I divide your 100% interest into 4 pieces and give them to you every 1 year divided by 4 period of time, which is 3 months. And now you might be seeing the pattern. It seems that dividing this 100% into smaller and smaller pieces and receiving more interest is the better way to do it. So you say, alright. But then he keeps going. So the question is, should you keep going? Should you keep accepting his higher and higher offers? And the second question is, if you keep accepting his higher and higher offers, will your money by the end of the year approach infinity or not? So I'm going to spoil the 2 questions for you. Question number 1 was, should you keep accepting his offers? And the answer is no, because if you keep wasting your time accepting his offers, by the end of the year you will still not have made a deal and thus will still be left with only $1. As for the second question, is the amount of money you will receive if you keep accepting his offers infinite? No. If you keep accepting his offers, at the end of the year, you will receive exactly $E in money. This is where E comes in. E is the special constant such that if you keep accepting this bank teller's offers, by the end of the year, you will be left with $E provided that you don't waste the whole year arguing with the guy on whether which offer would be better for you. So let's try to figure out what the formula for this number E is and how we can get it. The first thing is to consider what we are doing in order to get these numbers. What did we do to get $2? What did we do to get $2.25? What did we do to get this number of dollars? What we did was multiply our $1 by a certain factor. In this case, the first thing we had to do for a 1 per annum 100% is to take our $1 and multiply it by a factor of 1, which is the original amount we had, plus our percentage of amount that we gain divide by the total amount, which for this thing is still also 100%. Over here, we had to do a 50% of a total 100%, but we had to do it twice. So really what we did here was take 50% of 100% and squared. We did it twice. Similarly for offer number 3, this time I actually put it in the square form, cube form in this case. What we had to do to get 33% 3 times per year, as in every 4 months, is to take our initial amount of $1 and then multiply it by our initial amount, which is 1 plus the amount that we gain, divide by 100% to the corresponding number of powers that we divided our number into. So here what we actually have is a multiplication of $1 by a factor of 1 plus the number of years, number of pieces that you divide the year into, which is 1 divided by n. If you take the 100% and you break the 100% into n number of pieces, each piece is 100% divided by n, and 100% is just 1. So really the amount that we have to put here is 1 divided by n. And how many times do we have to compound this interest? Well, n number of times. So really the formula we are looking for is this. We have to take our $1 and multiply it by 1 plus 1 divided by n to the power of n, where n is the number of segments that we cut the year into. So in this case, if I eliminate this one here, because this one is actually not relevant to our thing, it's just the base starting amount, we want to figure out exactly how much our money will grow at the end of the year and what E is. So here, E is actually the limit as this n goes to infinity of 1 plus 1 divided by n to the power of n. As I said, if you keep accepting this guy's offers, i.e. you keep breaking the year into smaller and smaller pieces and then accepting his offer, where he multiplies your money every 1 year divided by n a period of time by a factor of 1 plus 100% divided by n, this is what you're eventually going to end up with. The limit as n approaches infinity, as in when we make n really big, which is the same thing as accepting the guy's offers over and over again, the value of 1 plus 1 divided by n to the power of n. So you might think, well, that's easy. I can just evaluate this thing. If I do 1 plus 1 divided by infinity to the power of, infinity to the power of infinity, I should get the answer. So you might think, well, 1 divided by infinity is like 1 divided by a really big number, so this must be 0. And then 1 to the power of infinity is just 1. But e is obviously not 1. E is some large number of 2.7 and then 1828, 1828 and so on. This number is special. Special not only because it's the amount of money you would get if you kept accepting the bank teller's offer over and over again. It is the number such that e to the power of x's derivative is itself e to the x. Now, we are not going to go into derivatives in this lesson. We are not going to do it. This is not even a lesson. It's just an exploration of e. But this is one of the interesting properties of this number. Before we get into all of that, however, let's try to write this thing in a formula that is not a limit of 1 to the power of infinity as apparent here. It is not in fact 1 to the power of infinity. There's something else happening here which we can see if we write this term here in a different form. So let's do that. On a new page, let's rewrite that e is the limit as n approaches infinity of 1 plus 1 divided by n to the power of n. You might know what a plus b to the power of n is. A plus b to the power of n by the binomial formula is the sum as r goes from 0 to n of n choose r times a to the r times b to the n minus r. This is the binomial formula. Given any two terms a and b, adding a to b and then taking that whole thing to the power of n, what you get is equivalent to the sum of all the terms n choose r, a to the r, b to the n minus r, 4 r's going from 0 up to n. Using this, we can write 1 plus 1 divided by n in a similar way to the power of n. This is the sum as r goes from 0 to n of n choose r. In this case, I will write a as being 1 divided by n and I will write b as being 1. In which case, what we have here is 1 divided by n to the power of r times 1 to the power of n minus r, which I will directly cancel off because for any n minus r, 1 to the power of n minus r is just going to be 1. And multiplying anything by 1 is going to give us the same value, so I really don't need to write that 1. So we're going to cut it. So 1 plus 1 divided by n to the power of n is this sum right here. So e is the value as n approaches infinity of this sum, which is r equals 0 up to n of n choose r 1 divided by n, and instead here, actually I've made a mistake here, I've written n accidentally when I meant to write r here, 1 divided by n to the power of r. So here, taking this r inside using index rules, we can write that this is the same as 1 divided by n to the power of r. So e is the limit as some number n goes to infinity of the sum of r going to 0 up to n of n choose r times 1 divided by n to the power of r. If you don't know what the choose function is, the choose function is this. N choose r, sometimes written as n and r like this in a vertical bracket, something like this, is n factorial divided by r factorial times n minus r factorial. And here, this thing, if you write what factorial is, x factorial for integer x's is x times x minus 1 times x minus 2 dot 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 all the way down to the integer 1. So you subtract 1 each time, multiply all the integers starting from x all the way down to 1, and that product is what x factorial is for an integer x. So here we have a sum which appears to be infinite. We appear to be adding an infinite number of terms, and each of these terms can be expressed in a little different format that we can actually read using this formula here. So you might think that this sum is actually infinite. It is in fact not infinite, it is finite. It is 2.718281828 and so on, some more digits. And I'll put a little card up here to show you that E is finite, and you can go and click that and watch that. But for now, we're going to accept that E is this number 2.718281828 and so on. So now, if we use these two here that I've put in a box to simplify the above equation, we can write that E is the limit as n goes to infinity of the sum from r going to 0 up to n of n choose r is n factorial divided by r factorial times n minus r factorial times 1 divided by n to the power of r. So now I'm going to use the factorial expansion to expand n factorial and n minus r factorial. So E is the limit as n goes to infinity of the sum of all terms starting from r equals 0 up to n of n factorial is n times n minus 1 times n minus 2 times ... And actually somewhere in the middle here there's n minus r as well. And then there's n minus r minus 1 and so on up to 2 and 1. Actually here I'm actually going to write another term in front of here so that we can have a little bit easier time writing the final answer later. The term before the n minus r term is of course n minus r plus 1, because recall we are multiplying all the digits starting from n going down one by one, all the numbers starting from n going down by 1 each time, and the number that is going to be in front of n minus r is the number that's 1 greater than n minus r, so n minus r plus 1. And then we have to divide by, for now I'm going to leave r factorial as simply r factorial, and here n minus r factorial I'm going to write as n minus r times n minus r minus 1 times n minus r minus 2 ... all the way down to 2 and 1. And then on the end here, let's not forget, there's another 1 divided by n to the power of r that we have to write down. So the reason I actually wrote these terms in the middle here is because there's some cancellation that occurs. You can see here on the new denominator there's a n minus r, and on the numerator there's also an n minus r. On the denominator there's n minus r minus 1. Similarly here there's n minus r minus 1. There's n minus r minus 2 right here, and cancelling all these other terms, we are left with a certain reduced amount of terms. If I write those terms down, we have E is equal to the limit as n goes to infinity of the sum, so r goes from 0 up to n of n times n minus 1 times n minus 2, I'll write that one as well, all the way down until n minus r plus 1. This whole thing is to then be divided by r factorial and n to the power of r. So we have this. Now I'm going to do a little something where I take this n to the power of r and distribute it among each of all of these terms. So to distribute these n to the r terms, what I'm going to do is consider how many terms are there on the top. If this first term is the first term, and that means this is 1, the next term after that would be this term number 2, the next term would be term number 3, and so on, up to the kth term, let's say, over here. So that means there are a total of k terms in the numerator up here. So, considering this, the first term is n minus r plus 1. The term next to it would be n minus r plus 1 plus another 1, or n minus r plus 2. The next term after that would be n minus r plus 3. You can see a pattern here that the first term is n minus r plus 1, the second term would be n minus r plus 2, the third term would be n minus r plus 3, which means the kth term would be n minus r plus k. But we can see the kth term is n. So that must mean that n is equal to n minus r plus k. Subtracting an n from both sides, we say that 0 is equal to negative r plus k, meaning that k is equal to r. So, how many terms are there on the numerator? There are exactly r terms on the numerator. What does n to the power of r mean? Well, since r is an integer here, n to the power of r means we multiply n by itself r number of times. So that means there are r number of n's on the denominator. So what I'm going to do is I'm going to pair the r number of n's on the denominator with each of these terms in our factorial on the top. So doing that, we get that e is equal to the limit as n goes to infinity of the sum of terms r equals 0 up to n of, I'm going to pair each of these n to the power of r n's with each of the terms on the top. So for the first term we get n divided by n. For the second term we get n minus 1 divided by n. For the third term we get n minus 2 divided by n, and so on for all the terms until n minus r plus 1 divided by n. And then there's an extra 1 divided by r factorial that we have to not forget. This thing's still there, so we have 1 divided by r factorial. But now we've distributed the n to the power of r among each of these terms here. So if I write this, e is equal to the limit as n goes to infinity of the sum r equals 0 up to n of, the first term is 1, the second term is n minus 1 divided by n, the next term is n minus 2 divided by n, n minus 2 divided by n, and then so on until n minus r plus 1 divided by n. The whole thing times 1 divided by r factorial. So we're going to use an interesting point here, the fact that because n is approaching infinity, this and this are very big numbers. This and this are very big numbers. Similarly, compared to r, this and this are also very big numbers. So what this means is we have 1 times a big number minus 1 divided by a big number. Here we have a big number minus 2 divided by a big number. And for all of these terms we have something like that. And then at the very last we have a big number minus some smaller number divided by a big number, where these two big numbers n is approaching infinity. So if we consider what happens when n goes from a small number to a big number, let's start n at something like 6. So if n was 6, we would have something like 6 minus 1 divided by 6 as the very first term here. This would be 5 divided by 6, which is 0.83 repeating. If we instead take n to be a bigger number, let's say 100, 100 minus 1 divided by 100 is 99 divided by 100, or 0.99, much closer to 1. If I consider even bigger number, like let's say 10,000 here, if I consider 10,000 minus 1 divided by 10,000, this is 9,999 divided by 10,000, which is 0.9999, very close to 1. In fact, as this number becomes very big, as it approaches infinity, the other numbers tend to become irrelevant. This minus 1 becomes irrelevant, and n minus 1 divided by n is almost equal to n divided by n. In fact, as n goes to infinity, n minus 1 divided by n approaches 1. The same is true for all of these other terms here. All of these other terms, as n approaches infinity, these all approach 1. This approaches 1, this approaches 1, this approaches 1. So what we have here is a bunch of terms that are all approaching 1, being multiplied by each other, and then being additionally multiplied by 1 divided by r factorial. So if we consider that, this means that we have the limit as n goes to infinity of the sum of r equals 0 up to n of a bunch of numbers that are all basically 1 when n gets really big. So we can kind of say that this is 1 times 1 times 1 times ... a bunch of ones approximately. Well, it is an approximation, but the approximation gets closer to an exact value as n gets really big. So as n approaches infinity, all of these values are in fact just 1, and then multiplied by 1 divided by r factorial. So all of these multiplied by 1s we can kind of get rid of, which means that e is in fact the limit as n approaches infinity of the sum r equals 0 up to n of all of these ones go away, leaving us with just 1 divided by r factorial. So now we have something that we can actually understand. Quite simply, if we have this thing, we can say that e is equal to, as n goes to infinity, what we have here is the sum from r equals 0 up to infinity in integer steps, of course, of 1 divided by r factorial. So then, Using this and substituting the values, we can see that E is equal to, and here what we mean by the sum as r goes from 0 up to infinity of 1 divided by r factorial is for every possible integer value of r starting from 0 to 1 to 2 to 3, all of those, we take that value, substitute it into the equation we see in front, and then write that value and sum all of those values together. So what we mean by the sum as r goes from 0 to infinity of 1 divided by r factorial is 1 divided by the first value of r factorial, which is 0 factorial, plus 1 divided by the value of r, the next value of r, which is 1, so 1 factorial, plus, and then the next value of r after 1 will be 2, so it's 1 divided by 2 factorial, plus the next value of r after that is going to be 3, so if you have 1 divided by 3 factorial, plus, and then 1 divided by 4 factorial, and so on. So in fact, E is equal to this sum here. Now it's important for you to note 0 factorial is equal to 1. If you want a proof of this, well, we can do a quick one here. I told you that x factorial is equal to x times x minus 1 times x minus 2 all the way down until 2 and 1. We could write this in a different way and say that x factorial divided by x is equal to x minus 1 times x minus 2 dot 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 all the way down to 2 times 1. What is this thing on the right here? Well, this thing on the right is x minus 1 times all the numbers, all the integers that are less than x minus 1 until 1. So this is actually also x minus 1 factorial. So we have that any x factorial divided by x is equal to x minus 1 factorial. Using this property, if we substitute 0 into here, we can agree that 1 factorial is equal to 1. Using this, if we substitute that into here, then 1 minus 1 factorial, i.e. 0 factorial, must be equal to this thing, which is 1 factorial divided by 1, which is 1 factorial is 1, so we have 1 divided by 1, which is 1. Therefore 0 factorial is equal to 1. Due to this reasoning, 0 factorial is equal to 1, and what we have in the end here, if I just erase this short work, what we have is that E, the mathematical constant E, is equal to the sum 1 plus 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial plus, and so on, for all the integer factorials going up from 1, 2, 3, 4 and so on. This is one way to write the value of E. So this is actually not where we have to end here. There's actually more stuff to discuss. I'm only going to discuss one of the other interesting properties of E, and that is the property of e to the x and its derivative. So with this is E. This summation here is E. Let's now consider what e to some power x would be, and let's just say x not equal to 0. So we'll say 4x not equal to 0. There is a 4x equal to 0 also of course, but for our purposes let's try to first make x not equal to 0 so that we can have some nice things happen. So e to the x is what? It is the limit as n goes to infinity of 1 plus 1 divided by n to the power of n. So then e to the x would be that thing raised to the power of x. So we have e to the x is, in here we have taken the limit and then taken a power. In fact, taking the limit and then taking the power is same as in this case taking the power and then taking the limit. So we can actually bring this limit outside of this this bracket here and say that this is also equal to the limit as n approaches infinity of 1 plus 1 divided by n to the power of n to the power of x. Then using index rules we can see this is equal to the limit as n approaches infinity of 1 plus 1 divided by n to the power of nx. If you have any problem with this, you can see we can take this into here. Anything to the power of a to the power of b is equal to that same thing to the power of ab, which is what's happening here, which is why this is nx. Now let's say let some other variable which I'm going to be calling m be equal to n times x, which then means that n is equal to m divided by x. So let's try to substitute this new variable which we've just defined into this above function here. So that means that e to the x is equal to the limit as n approaches infinity of 1 plus 1 divided by, instead of n, let's substitute m. So we have m divided by x to the power of, here nx is equal to m, so to the power of m. Now here we could have also substituted n in the limit as m divided by x. So we have m divided by x here. So therefore e to the x is the limit as m divided by x approaches infinity of 1 plus 1 divided by m divided by x whole thing to the power of m. Rearranging things a little bit so that they become nicer, this is the limit as m divided by x goes to infinity of 1 plus x divided by m to the power of m. Now there's one last thing we're going to do. Since x is some fixed value in this context, because x is fixed, the limit as m divided by x approaches infinity is identical to finding the limit as m approaches infinity, because m divided by x approaching infinity and m approaching infinity are the same thing. Why? Because, well, x is some fixed number. It is some fixed number that is not changing. So the only way that m divided by x can approach infinity is if the only changing variable, which is m, approaches infinity. So therefore we can replace this and say that e to the power of x is equal to the limit as m approaches infinity of 1 plus x divided by m to the power of m. This is now what e to the power of x is. So you'll notice something interesting here. E by itself is this thing. Where is it? Somewhere up here, I think. E by itself is this. But when you have e to the power of x, as in you multiply e by itself multiple times, you just have to put that power and substitute it into here. So this is e to the power of x. Now, by doing the same exact method that we just did to convert e to the power of 1 as in e into a sum of factorials like this, if we want to convert e to the power of x, we can do it in a similar method. We can do it, and here I'll just actually run through what we're going to have to do. We're going to first have to write this in the binomial form, so we're going to write that e to the x is the limit as m approaches infinity of the sum as r going from 0 up to m of, in this case, 1 plus x divided by m to the power of m is, actually I'll do it without the bracket, m choose r times a. In this case we're going to put a as being x divided by m, so that is x divided by m to the power of r times, and over here we're going to have 1, which is here 1 to the power of m minus r, which I'm going to cut because 1 times anything is just that same thing, and 1 to the power of m minus r is just 1. So we can cut that away, and then we have this thing. I'm going to skip a few steps here because we don't really need it, because we've already done it. E to the x is the limit as m approaches infinity. If you want those steps, of course you can go up and look at what we did for when we didn't have e to the power of x. So this is the sum as r goes from 0 up to m of doing that simplification of m choose r, where we do m factorial divided by r factorial, m minus r factorial, and then we do all of those cutting of terms. What we eventually end up with is m times m minus 1 times m minus 2 ... until m minus r plus 1. This is then divided by, here in this case, in this case it's m to the power of r, and then we have another x to the power of r over here, because now recall, this time we have an x to the power of r. When we do x divided by m to the power of r, it is x to the power of r divided by m to the power of r. And that we get up to here, divide by r factorial over here, because recall, m, choose r, is m factorial divided by r factorial, m minus r factorial. These two terms are what gave us all of this set, and the remaining r factorial I almost forgot to write, it is also there. So we have this. Now again, considering the fact that over here there are r total terms, and I can distribute this m to the power of r, which is just m multiplied by itself r number of times among each of them. We can then write e to the x as the limit as m approaches infinity of the sum of r going from 0 up to m of m divided by m plus, actually not plus, times m minus 1 divided by m times m minus 2 divided by m, all the way down to m minus r plus 1 divided by m, and then times x to the r divided by r factorial. So here, each of these terms, as m goes to infinity, each of these terms is going to approach 1, which means that the whole product of the terms is going to approach 1. So then, as this product of terms approaches 1, we can see that e to the x is the limit as m goes to infinity of the sum of r going from 0 up to m of simply x to the r divided by r factorial. So now, if we consider what this means that we need to sum all the r's from 0 up to infinity of x to the power of r divided by r factorial. So what this means is we need to do e to the x as x to the power of r, first r is going to be equal to 0, so x to the power of 0 divided by r factorial, which is 0 factorial, plus the next value of r is going to be 1, so then that means x to the 1 divided by 1 factorial, plus the next value of r is going to be 2, so x to the 2 or x squared divided by 2 factorial. The next value is going to be 3, so x cubed divided by 3 factorial, dot 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 all the way down. We are also going to make this x to the 0 become 1. Now here, this is one of the reasons why I didn't want x to be 0, because if x is 0, then we don't have a real answer for the 0 to the power of 0. If we put 0 to the power of 0 equaling 1, we do in fact get the correct answer of e to the x. In the case of e to the 0 is equal to 1. However, because I want to avoid dealing with 0 to the power of 0, I just told you that x is not equal to 0 above. So having that, now we can say that e to the x is equal to, this is 1, cancelling them we just have a 1, plus x to the power of 1 I'm just going to write as x, and then this divide by 1 factorial is 1, so I'm not going to write it, and then plus, here we have x squared divided by 2 factorial, x cubed divided by 3 factorial, the next term after this would be x to the 4th power divided by 4 factorial, and so on. So therefore, e to the power of x can also be written as a nice sum. It is written as 1 plus x squared divided by 2 plus x cubed divided by 3 plus x to the power of 4 divided by 4. Meaning, you can very easily find what value of e to the x is by simply computing this infinite sum. Very easy. So now, this leads us to the final interesting property, which is what we get if we take the derivative of e to the power of x dx. Some of you might not know what a derivative is or how to take a derivative, but I'm going to tell you just one simple thing. The derivative of x to the power of n with respect to dx is n times x to the power of n minus 1. I'm going to leave you only with this. If you want to learn about derivatives, I probably have a derivative video out on my channel, or you can find it from somewhere else. Learn what derivatives are. They're quite useful and quite important. But for now, we're going to keep this on the side, maybe over here. The derivative of x to the power of some n dx is equal to n times x to the power of n minus 1. So taking the derivative of the left hand side and the right hand side, the derivative of the left hand side I'm going to label as derivative of e to the x with respect to dx, as in x. On the right hand side, we have the derivative of 1 dx plus the derivative of x dx plus the derivative of x squared dx plus the derivative of x cubed dx derivative of x cubed dx, all divided by the respective factorials, which in this case for the first two we don't have, but this is divided by 0 factorial and this is divided by 1 factorial. This is divided by 2 factorial, this is divided by 3 factorial, and the next one I'll write also dx to the fourth divided by dx by 4 factorial, and so on. So in this case, using this formula we have here, for the derivative of x to the power of n dx, we can write each of these terms. The derivative of e to the power of x dx is equal to 1 is x to the power of 0 for x not equal to 0, which means that here what we have is x to the power of 0, which then becomes 0 times x to the power of negative 1, i.e. 0. So the first term, the very first term here gives us 0. So here 0 plus the second term is the derivative of x with respect to x. Here x is x to the power of 1, which then converts into, by this formula, the 1 goes here and we get x to the 1 minus 1. So this is 1 times x to the 1 minus 1, which is 1 times x to the 0, which is just 1. So the second term gives us 1. The third term gives us the derivative of x squared dx divided by 2 factorial. X squared gives us 2 times x to the 2 minus 1, which is x to the 1, which is just 2x. And then 2x divided by 2 factorial is going to give us x divided by 1 factorial. So here we have x divided by 1 factorial, which I'm going to write as x. The next term is the derivative of x cubed dx, which is going to give us 3 times x to the 3 minus 1, which is 2, and then that has to then be divided by 3 factorial. So here dividing a certain number by its corresponding factorial will give us the n minus 1th factorial. So here dividing 3 by 3 factorial will give us 1 divided by 3 minus 1 factorial, which is 1 divided by 2 factorial. So then the next term is going to be x squared divided by 2 factorial. Similarly, for the next term, I'll do it for one more term and then you will see the pattern. The next term is the derivative of x to the fourth divided by 4 factorial. The derivative of x to the fourth dx is equal to 4 times x to the 4 minus 3, 4 minus 1, which is 3, so x cubed. This thing 4x cubed then divided by 4 factorial is going to give us x cubed divided by 4 minus 1 factorial, which is x cubed divided by 3 factorial. So we have x cubed divided by 3 factorial. Now you can probably see the pattern. The next term after this is going to be x to the 4th divided by 4 factorial, x to the 4th divided by 4 factorial, and so on. Now notice, what we have here is 0 plus 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on. What was e to the x? Well, e to the x was 1 plus x squared divided by 2 factorial plus, oh, wait a second, this is also e to the power of x. So therefore, the derivative of e to the power of x dx is also e to the power of x. Now, this might not seem that significant if you are not familiar with calculus, and yes, I agree, I should have probably taught you calculus before, or you should have probably learned calculus before you came to this video, because otherwise this would not make sense to you. But for those of you who know calculus, you might understand this is something special. The derivative of this function, the derivative of e to the power of x dx, is itself the derivative of e to the power of x dx is itself e to the power of x, which is an interesting property, and in fact this function is one of the only functions that has this property. Of course, in general, derivative of some constant times e to the power of x dx is equal to itself as a constant times e to the power of x, but e to the power of x on its own is the special thing that's happening here. The derivative of e to the power of x is e to the power of x, which is the special thing happening here. This is another one of the special properties of the value e. There are a bunch more which I cannot cover in this video because this video is already getting too long. I will mention another one of them which I really like, and we will conclude this video. Another one that I really like, which is very special and very important to all of mathematics, is the identity that e to the I theta is equal to cos theta plus I sin theta, where I is the imaginary unit of the square root of -1, i.e. I squared is the value such that I is the value such that I squared is equal to -1. This is another important identity. We can derive this from the Taylor series of cosine theta and sin theta, and I'll probably put another video where I do that. But for now I will leave you with this. You can search this on YouTube if you're interested, or I might produce a video on this, in which case it will be there in the end title screen of this video. And that is all I would like to talk about e to the x. I hope you got some understanding about e to the x. There's a lot to cover. This is a very special number, very important and very close to my heart. I like this number, and I hope after this video you do too. If you want, feel free to browse the rest of my channel as well, and subscribe, like and share my videos if you like them. And thank you for watching, and goodbye.